And we're live. Welcome everyone to the 10th teardown in this series. I'm super excited. I'm here with, we're going to call them the teardown trifecta, Chris and Molly. We'll introduce ourselves more later. We're going to wait a few minutes for the rest of the crowd to roll in. While we're waiting here, please introduce yourself down in the chat. So down in the lower right, you do have to fight with Zoom a little bit and switch that blue box to send to everyone. Otherwise, you're just pinging us. So introduce yourself. And today we're talking about the Fitbit and in particular about batteries. So introduce yourself and tell us what your first experience was, either designing or hopefully not having any failures with battery design. So let's kick it off from our side. Maybe Molly, what do you got?
Yeah, my first big foray into battery design was working on the Google Pixelbook Go laptop. And I was the product design DRI for the cell design for that, as well as the pack design. So definitely, I mean, a lot of our issues around batteries were actually more about getting the battery cells to stick consistently to the magnesium housing. So we did a lot of explorations around adhesives, different adhesive types. That was a big topic for that program. Yeah, I'll pass over to Chris on your first foray into battery design.
Yeah, I think when I first started at Amazon, we were designing the Kindle 2, and we started with, I guess, sort of these pack design, like off-the-shelf almost components, and they had like a plastic frame around them, and then some like metal shielding around the outside. And then as we got, further down the line and a couple more products, and they were like, actually, we want to make these as thin as possible. So get rid of all that stuff and just put the bare cell on there. And so, yeah, we had to change the way we adhere things. There's no longer like plastic tabs that hook and rotate down. You just screw them in. You have to tape them or glue them or do something else. And so it became a lot harder to design around, for sure. How about you, Tobias?
Yeah, so the first thing that comes to mind, actually, fortunately or unfortunately, I didn't have that much direct exposure to the battery design during my tenure at Apple. The one situation that comes to mind was kind of a scary situation around devices overheating in an early prototype build. And everybody thought it was the battery causing some type of overheating. After a bunch of different failure analysis, we actually root caused it to the charging coil. This is the inductive charging coil on the back of the watch. And there was some bizarre, extremely low failure rates. It was defects in the flex that were causing shorting when they were assembled into the back crystal in a certain way. And it was an intermittent situation, so it would heat up for a few seconds, but then it was very difficult to reproduce. So it was very scary. Tons of effort went into resolving that, as well as putting in place safety precautions so that it wouldn't happen again. But that was kind of the one thing that stuck out to me when I think about batteries and thermal runaway events. All right, so welcome. Let's get things kicked off here. So welcome again to, this is our 10th teardown, which is super exciting. Change notice on Snapped. What are we doing here? This is our monthly teardown series. We're talking about all things electronics, supply chain, manufacturing. So I see a lot of regulars here, so welcome back. And welcome again to the newcomers. So please introduce yourself in the chat and tell us about your first experience with battery design. Our goal here, we're building a community to share knowledge and support you guys for continuous improvement. One reminder first, actually, if you do need to duck out, please fill out that survey. Super valuable. It tells us what to tear down next and helps give feedback to our team. And I think, Molly, you have some announcements.
That's right. Actually, really exciting. So thanks, folks, for joining this, remote teardown. But we're excited to announce that the next teardown we'll do for next month in June will actually be in person in our Palo Alto headquarters. You can join. We'll be doing a teardown of the Amazon Echo Show 10. And we'll also do a bit of a happy hour networking kind of event too. And we'll have all the other, Tobias mentioned this is our 10th teardown. We'll have all those 10 different devices in our teardown playground so that people can come in, take a look at those parts, and we can all have conversations about what went on there. So we'll put a link to that. That's in the chat. You can go ahead and register. We would love to see you all in person there. And then the second announcement that I have is, if you haven't already seen it, Anna, our CEO, was recently interviewed on Jacob Goldstein's podcast called What's Your Problem? Really great overview of Anna, her story, instrumental, the problem that we're solving here, just collecting and processing all the data from manufacturing to solve problems. So I definitely recommend you guys tune into that, take a look at it. I found it to be a really fun summary of what we're doing. And so then before we dive into the Fitbit, just a chance for the three of us to all introduce ourselves. And I will start. I'm Molly. I'm a solutions architect here at Instrumental. That means I work with our customers on technical scoping of their programs and also the implementation piece. My background is in mechanical engineering. Before coming to Instrumental about 1.5 years ago, I was working at Google as a product design engineer, working on laptops and tablets, and have done some various other mechanical design consulting along the way in my career. So I'll pass off to Tobias for an introduction.
All right, thank you, Molly. I'm Tobias, background in mechanical engineering, product design. Spent about 6 years at Apple working on Apple Watch and iPhone. A lot of focus on health sensors and touch and display. And I've been at Instrumental about 3 years, leading a variety of different teams. And I see some exciting backgrounds here. Looks like we've got some experience in the crowd, batteries on handheld radios and batteries on laptops. So I'm super excited to hear your theories and input about battery design when we dive in. But first, Chris.
Yeah, my name is Chris Lee. I'm a product designer and a mechanical engineer. My background was having worked at Amazon on several generations of the Kindle for about 7 years, went to a couple of startups, and most recently I'm at a self-driving or autonomous tractor startup. So doing very different things, but still in the realm of mechanical engineering. So while I have you guys here, I'm going to go ahead and share my screen and we'll get into the teardown. So first we'll give just a brief overview of why we picked the Fitbit Ionic. As Tobias mentioned, we do these surveys at the end of this session, and a lot of people were asking about smartwatches. So we're thinking about what smartwatches do, and we heard about some kind of hot news, I guess, about this Fitbit Ionic, which was stopped production maybe a couple of years ago, and thought it might be interesting to take a look at some of the choices they made in the product, and maybe, some of the things that you're hearing about now, the battery and why maybe it's getting so hot. We actually purchased these off of eBay, so they're secondhand devices. We have, we're just gonna take a look inside. So that's, go ahead, Tobias.
Yeah, no, I'll jump in here while you get ready to dive inside, Chris. This, like all the other teardowns, we just want to make it clear that we don't have any inside knowledge on these devices. So we're leveraging our combined product design backgrounds to speculate on a lot of these theories, which I think the goal here is really that you guys can take away some best practices when it comes to battery design and things that you guys should be thinking about for the products that you're designing. So let's dive into it.
All right. So so this is the Fitbit Ionic. We don't have the bands, but basically all the good stuff is here. And it's one of Fitbit's earliest really high-end smartwatches. I think it was designed to compete against the Apple Watch, which Tobias has a little bit of experience with. But it has this really sleek all aluminum frame with a couple of really interesting sort of plastic bands on the outside. It's got the heart rate monitor on the back, the charging pins. I think this one came with an NFC antenna, and was their response to like Fitbit Pay. And I don't know if I can show it here. I think there's an ambient light sensor as well. This product was designed to be water resistant up to 50 meters. And And just as a quick disclaimer here, this cover lens, in a nod to that water resistance, was extremely difficult to take off. So we actually did that a little bit beforehand by applying some heat and some prying. You see, I think we actually cracked one of the corners here. But yeah, so if I just take that out, I kind of reveal some of the guts already. And I think this looks like the NFC antenna right here. And yeah, actually, if I zoom in a little closer, you can see some of that adhesive around that around the edge, which is pretty beefy, and it's still stuck on to mostly to this to the frame.
We had Chris. We actually got a few questions here.
Oh, go ahead.
On the waterproofing. Mark
yeah.
and Karen all are interested in what the waterproofing design looks like for this Fitbit. So what kind of adhesive, you mentioned that it was pretty tough to take that display cover glass off. Can you tell us what kind of adhesive you think was holding that on? Because again, the adhesive around the cover glass is typically one of the hardest parts to get a consistent seal on.
For sure. Yeah, I mean, I think some of this adhesive, like there's a couple of different types that people might be familiar with. There's like liquid glues or epoxies. There's sort of pressure sensitive adhesives. There's also some interesting ones like heat activated adhesives, which kind of start out without much adherence at all, and then you like heat them up and they like bond solidly. But if I take a look at this, it looks like a die cut. Doesn't look like a liquid glue, just because I can see some pretty straight edges and there's no overflow around the outside. So I would suspect this is some kind of PSA or maybe heat activated PSA. I don't know, Tobias or Molly, what do you guys think?
So it was definitely harder to get off than a standard PSA. We use, what you didn't see here was the heat gun that we used multiple times to heat up that display to try to get this off. And so from my experience, it was definitely stronger than just a standard pressure only adhesive. So my best guess is, I think, similar to Chris, around an initial press on some type of die cut adhesive that was further cured with heat. And the tricky part there is, how do you heat up that PSA without damaging the display? So you have to get into kind of more advanced pressing fixtures that heat up around the edge of the display only. Anyone in the audience have other experience with adhesives that can provide the best water seal or the most reliable water seal? And Molly, I don't know if you have anything to add on your best or worst adhesive experience.
Yeah, no, I was just thinking we could actually hop into the app and we can kind of show what that adhesive pattern looks like, and people can weigh in on that as well. That sounds
great, because it's really hard to show here. So why don't we zoom in through instrumental?
Cool. All right. So this is the same. First, this is the instrumental web app platform. So basically what we provide is a place for people to both store all of the images and functional test data, measurements from their manufacturing builds through development and mass production. But then we also provide AI tools that help people actually sift through all that data, solve problems through manufacturing, and drive things to closure. So we are going to be showing off just a small portion of that functionality right here, but later on we actually will do a demo to show some of the other functionality. Right now we're basically just going to be using it to see these really high resolution images of the Fitbit. So this is basically the same scene that Chris was just showing, and we can zoom in to take a look at what this adhesive looks like, if this helps anyone's theories.
Yeah, Ron was mentioning that potentially it's a heat activated film if it's not super tacky. Chris, can you tell how tacky it is? I think it wasn't extremely tacky, but it wasn't rigid. My experience with heat activated films is it's almost like an epoxy in a die cut form, and it gets extremely rigid after it's fully cured.
This one still feels, it's not tacky, but it almost feels like a silicone kind of stretchy, I don't know, sensation. So I don't know if it might be some kind of hybrid. Maybe I think I'm leaning closer to, it's not like a hard thing now, or it's not like, it's still trying to stick to the plastic, and I can peel it back. But yeah, I don't know. I don't have as much experience with the heat activated adhesive. So that's something that it could be.
The other interesting point for water sealing is, Chris, I believe there's an antenna split, a plastic to metal seal on the housing there, which I would be concerned about for water sealing. How do you think they did that? Or can you tell us what you see from the device right now?
Yeah, I'm in this image, actually, I think if Molly, if you can zoom into the top or bottom corner, you can actually see the plastic kind of comes and joins through the metal bits, and actually that entire top surface is all plastic. So I don't think they had to seal like between two different disparate materials. And looking at how tightly that's bonded, I think they probably did some kind of really integrated insert molding. I've heard of like nano molding, maybe, where they etch the surface of the metal to get an even tighter bond between the plastic kind of fills in some of those bonds as it's melted in there. So I think that might be how they're providing a complete single surface, single material surface for that water seal of the display.
Great. Well, Molly, let's keep going and tell us what we're seeing on the inside here.
Yeah, so this is the NFC antenna, pretty big antenna, really. So I guess my understanding is this is basically to enable Fitbit Pay. Are there other things that they're doing with this NFC antenna? If anyone wants to chime in on the chat with ideas there, or Chris or Tobias, if you guys have any ideas about that.
I always thought like NFC would be a great way to pair. So you just it knows like its serial number, and you could just like hold it up to your phone. But I don't know if they ever enabled that, or if, since it probably has Bluetooth or Wi-Fi, they probably just do that. I don't know, Tobias, what do you think?
It's my initial reaction is, wow, that's a large NFC antenna. And I'm not extremely familiar with NFC antenna designs, more so with like the Wi-Fi, Bluetooth, LTE. But I believe maybe this was in the earlier days when a larger design was required, because in the Apple Watch days, I think we got it a little bit smaller, tucked away in certain areas. And there was always a debate about what can you do with NFC, but I always remember payment systems was the primary driver.
Yep. All right, so if we peel that back, and now we are looking at these display connections. So I see kind of 1, 2, 3 flexes coming out of the display. I'd be interested to see kind of what people think each of the different signals these are carrying are. Tobias, you probably have some input here on from your display expertise.
I've got some guesses here. I also have my turned down Fitbit. Would love to hear from the audience too. If you guys can tell just from the image, 3 flexes, and I believe this is an LCD screen, so not an integrated OLED. The fat one there is likely the LCD, fat one in the middle. The one right below it with the 4 traces, that's probably the backlight. All right, Aaron's on the right track here. We got touch backlight LCD. And I think I agree with Aaron here. That top one is the touch flex. You can tell it's closest to the cover glass if you look at the side. And I think you can't really see it here. There's actually a small ambient light sensor on the display that also feeds into that touch flex.
And this one is actually hotbarred, I think, into the display flex.
Yeah, so they don't need to, they can save a connector there. So I think that makes a lot of sense.
Yep, it does make sense. Okay, so we'll peel one more layer back here. And one thing that I thought was interesting here was actually these buttons. So you can see, on this device, we have 3 buttons, probably something like power, maybe some ability to navigate or volume. And if we zoom in on this, what we can see are these buttons. We can see, you know, the piece that's actually attached to the outside there. And then what I was curious about though is that it's almost like a side mounted button component. It looks like we don't see any connections on this side of the board. So what do people think is going on there? Again, put your ideas in the chat, and we'll hear what Tobias and Chris think too.
That's a funky one. It's hard to tell from this angle. I can't see where the connection is of that button. So either it's connected to some other board underneath this main PCB, or somehow there's a connection on the backside of this PCB. That's my best guess.
Yeah, I mean, I think what I like about this button design is sometimes you see like surface mount buttons and you're pressing in all the time with the buttons on the outside, and so you get sort of a strain or a stress that goes across it. But this one, the button seems to be, you know, bottoming out maybe on the board itself, so it can't actually move and twist too far. So I would suspect there's some, like Tobias mentioned, maybe there's something, maybe it's just in the reverse side, and it's just mounted that way. But yeah, I like this design because it prevents it from moving too much and shearing off.
Yep, that makes sense. The other thing, I know we have a focus on battery today. So we basically, I can see two other, now we've removed the display and touch connections. I see two other flexes here. I see this kind of smaller connector up top, and then I also see this larger connector down here. And so hoping to hear people's predictions on which one of these has to be battery, right? And then not sure exactly what that other connector is, but would love to get people's thoughts here. What are we seeing in the chat?
What do you guys think that final connector is? And I think maybe let's go back to Chris, because I know people are excited to get down to the battery here. And I think if we take off that board, we'll actually be able to see where those connectors are going.
Yeah, so I've took out the display. Here you can see those flexes that we we're talking about, and yep, this one is hot wired on together, so you can see that. Also, you can see some of this stuff was peeling off on that display. It is very stretchy, so that's another interesting thing there. But yeah, I just took off these two flexes and some of the other components, and we'll see if we can get this board out of here.
We got a few questions coming in here that we can address. So we had one from Jacob around general thermal management, around how is the heat from ICs, batteries dealt with in these small devices to avoid hotspots versus larger devices when there's more room to spread. I can share my thought. We'd love to hear everyone else's thoughts as well. I know on some of the past devices that we've torn down, maybe we can show some of those at the end. There was a huge focus on thermal management. I think in the DJI drone, you could see heat spreaders and thermal paste everywhere. In the Mac Studio last month, wow, that was like at least 50% of the entire volume was taken up. The primary driver of heat, I see the battery there, is around those processing units, this producing a ton of heat. And my assumption for a device like this is the processor is probably not producing an insane amount of heat. So we'll talk about the battery and how heat affects that during the charging cycles. But I think during everyday operation, because it's not a processor intensive device, I don't think that's probably how they get away with more of a minimalist thermal design. I don't know if Molly or Chris have any other thoughts on that.
Yeah, I think in my experience, like the tablet to laptop space, you see like active cooling starting to come in, and a lot more focus around thermal management starting with laptops. So that doesn't surprise me too much to hear your experience that way, Tobias.
Yeah, I would agree. I think like in the Kindle, it basically doesn't process things for a lot of time. So we never really had to worry about thermal things, thermal management. Just even though it's a consumer electronic device, like it's designed to basically show the screen for minute at a time. So there's very little in the way of thermals that we had to consider. So it really depends on the application. And because the screen is so small and the processing of what it's actually doing is not that intensive, I agree that you don't really need to have a fan or anything else in there. It's got enough, this solid metal band and some other things that really help it dissipate any heat that it generates in normal conditions.
What do we have? What do we have here? I can't help but focusing on that round spot on top of the battery.
Yeah, so this is like a metal shield, and on the underside that we do have this the battery itself. But one unusual thing that I don't normally see is this is actually a punched hole through the top surface here, and they have, it's very intentional. They have the black shielding around, or black tape around it as well. So that is something interesting to take a look at. I don't know, maybe you can get to mine, and this is just the underside of the board as well, or under that, the rest of the housing. But maybe Molly, you can get a closer look at this, because it's going to be hard for me to hold it here all the time and keep switching it up and down.
So what does the audience think? Kind of the first two really interesting things here are there's this hole in the shield can over the battery. What do you guys think that is for? As well as what is the intention of the shield over the battery? Since we've also seen some devices where the battery is just adhered directly either to the PCB or some other part of the housing. Molly, what do you think?
Yeah, I mean, I'll just say first that as someone who worked on batteries, this makes me very nervous to have potentially a punching operation that may go in the direction into the battery pack. We obviously did a lot to make sure that we weren't designing anything that would have any sharp edges and that could potentially puncture the cell. So I'm not sure. I mean, one thing I know is kind of and if you were designing this with a focus around repairability in mind and being able to replace the battery pack quickly, that could be one reason to have this kind of a bracket. And then maybe that hole is because you have kind of adhesive, let's say, around the perimeter of the battery cell onto the shield. And this hole could help you get your finger in there to kind of punch that out. I don't know. It seems a little wacky though. Chris, what about you?
Yeah, I agree with a lot of those ideas. I think one other thing, because this whole structure looks like it might, the battery itself is usually made from like an aluminum pouch, and it's not grounded because it's insulated with like the plastic layers around it. Maybe it's this metal shield as a way to incorporate it better into the antenna subsystem. So it's like it's a guaranteed ground and metal plane. And you can see there's a lot of like gold contacts kind of on the upper side as well. So maybe there was something there with some antenna. I don't know what the hole would mean for that, but that's possible. Either that or maybe there's that foam there. So maybe because this has like a vibration motor, maybe there's a reason for it to need some isolation above the board so that it doesn't rattle against the board. But those would be the couple ideas there.
Yeah, Sam was asking that what's actually inside of that hole in the cutout. I believe it's a small foam, and we actually tested it to see if it was conductive. It's a non-conductive foam, but it is barely proud of that shield can. So again, one theory here as well was you wanted to ensure that any contact, Sam was asking what's on the other side of that. it is the main PCB backside, and it looks like there's a bunch of test points on that PCB. And so there could be a theory that you wanted to have in the case that there was incidental contact, either in a drop event or, as Chris was mentioning, during vibration, that you wanted to ensure that the first thing to contact was this small piece of foam rather than the rest of the battery or the shield cam.
Yeah, that's interesting. So with battery cells, you expect them to swell usually about 10% in Z over the lifetime of the battery in terms of its cycling. And that's just normal standard, something you always need to design for with these kind of batteries. So I know we always try to ask our battery team about like, can we predict exactly where the swell is going to happen so that we could design, our larger Z components kind of on the edges, because it might not swell as much there. And we typically see that it kind of swells most at the middle. Battery team would never sign on for that in my experience. It was always assume uniform Z swell of 10%. Some other things I thought were kind of interesting here. Maybe we can see it better from the other side. We can actually see that this shield, all these pieces, if we zoom in here, we can see all these weld points. So all of these individual, there's like a couple spring clips here for grounding. These are all little bits that are welded onto this frame, which is kind of interesting.
Why do you think they welded that instead of just folding them back and plating them or something like that? What was that all about?
I really don't know. Tobias, do you have any ideas?
My only guess here, again, on the theory that this shield can plays a critical role in the antenna architecture, which I think we can conclude it does play a critical role, whether that was the original design reason or rather it has a significant effect since it's a giant metal piece in the middle. They have all of these grounding points. So on the side there, as well as those little spring fingers on the top, they have the gold plating. And so my only thought would be if they were doing this plating process, but they didn't want to have to deal with masking and plating with a giant piece. And so they just wanted to plate, because they're doing this selective plating on each of those small tabs and then weld it all together. Would be great to get thoughts from the audience as well on why those were welded on instead of just stamped and formed as one part.
Yep.
So what else? We're talking, again, we're diving deep into batteries here, and we're talking about worst case scenario thermal runaway events. And there's a lot of things that we've heard from the audience that we're talking about here as what could potentially cause these type of events. You're talking about battery swell. I saw a lot of comments about battery swell here, how we can design for that. What are the other things? What are the other things that could cause, catastrophic failures that we should be thinking about?
Yeah, one thing that struck me is that something we always called out was the like dog ear edge folding. So obviously really critical that you're sealing the battery cell correctly. From what I can tell, actually, I may have even a better picture here. I'm looking at the folding sort of in these corners to make sure that's sort of folded in and down. And then up here, I also see similarly what I think is pretty industry standard good edge folding. And I think the double edge folding on the side was another thing that we called out. So those all look pretty good to me. What about this? I could imagine maybe the circuitry here, something could go wrong here. Chris, any ideas?
Yeah, I mean, I think that's a pretty standard feature as well on most pouch type batteries like this, or cell batteries, where it's like it's a battery management system, probably has some small circuitry on there to manage like maybe some temperature and some the charge cycles and keeping it at the rate of charge that it needs to go, and it might shut it down if it gets too hot. But I don't know if it can shut it down if it's like a rapid event or something catastrophic is happening. But that's just more for general things. And they kind of take advantage of that little ledge that's created when you do those dog ear folds.
Right. Another thing for kind of catastrophic events that comes to mind for me is really like the jelly roll internals.
Mm.
So they basically, take there's anode, cathode, and then there's separator layers in between those. If your separator layers get too thin and there's opportunity for anode and cathode to effectively make contact, that's obviously a catastrophic event. There also, a big concern was always contamination in that jelly roll as it gets inserted into the aluminum pouch. So,
Molly, can you explain like what a jelly roll, like how does it actually look inside, or what is going on in the
yeah,
battery? I don't think I've ever seen one.
yeah, you can almost think of like a fruit by the foot.
Okay.
Like you have that like
It's like,
thin non-conductive layer, and then you have layers where chemicals have been deposited, and those chemicals, my understanding is basically that's like what makes up the anode and the cathode is kind of the secret sauce of what battery cell vendors own. That's like their special IP. So they basically have what then forms like a layer, like think of a long fruit by the foot of like 5 layers, and you have like separator, anode, separator, cathode, separator. And then it's all very automated. These machines will basically, you can think about this like kind of XY shape. It'll roll it up like that. So it'll fit perfectly in here. And they put that into this like aluminum, thick aluminum foil pouch.
got it.
Yeah. So in that process, there's certainly potential for some contamination to get in there. And something that I saw was actually like a pretty standard process was to have cell teardowns be a part of the process of shipping goods. So they would ship the goods from the battery cell vendor, either to like a pack vendor to integrate with multiple cells, or potentially maybe here they would ship straight to FATP. And they would need to do some number of cell teardowns to be looking at the internals and making sure that everything looks right. There is no contamination, all these kind of things. And that was actually a really fascinating process because you had to get like a special certification to be able to do cell teardowns. It's not, you don't want just anyone to like rip these things open. Do not try this at home. We didn't do it here in our teardown. This was as far as we were willing to go from a safety standpoint. And but yeah, they basically went up on the rooftop of this vendor, and then they had little like rooms that were accessed only from the roof, and then there could only be a certain number of people in there, like 3 or 5 or something. It was pretty fascinating to see. So definitely these things, it can be really catastrophic. We would also do things like a puncture test where they basically drive a nail through the battery cell. And as you can imagine, that instantly creates contact between anode and cathode, and you do have explosions. I'm not really sure why they required that in the reliability testing. But definitely all these things are good things to think about in terms of how are you testing your batteries to make sure that you are ready for these corner cases, kind of edge cases that may come up, and how do you make sure you find those in development rather than finding them in the field or in mass production. Tobias, I know you mentioned some waterfalls that you talked about. You want to talk a little bit more about that?
Yeah, I think again, on the big buckets of failures, there's all these details that you're teaching us now about all the internal failure mechanisms. There's multiple buckets. We're going to talk about maybe punctures in a second, but really, how do you catch these early? Like Molly said, is you need to have proper tests in place, reliability tests. And again, a lot of these are corner scenarios where it goes through one maybe heat event and then a drop. And we actually have a great piece of content that we can probably drop in here that outlines all of these different reliability tests. It's a reliability test suite. So we can post that in the chat. Highly recommend taking a look and comparing against what your current test suite is to make sure that you identify in development any of these corner case scenarios. On the topic of the different types of failures that could lead to this thermal runaway, we've got these internal battery quality issues. We talked about standard thermal swell and design and how the spacing around the battery affects. You also mentioned, Molly, the puncture test. What, like, looking at the design here or what's around the battery, is there anything that you see that's at risk for some type of acute puncture of this cell?
Yeah, so I mean, we can see this. This is kind of a spacer that gets adhered to the cell here, just like a thin plastic piece. Let's take a look at what that would be contacting, because that to me is kind of a sign that there's something there. So I think to do that, we need to go here. This would be the side that piece would interface with. Actually, even one step ahead, because there's also some magnets that are held down in here. So I think that spacer lines up here with these charging contacts.
Looks like it, yeah.
That does seem like something that I wouldn't want next to my battery, but at least they do have that die cut in there that will hopefully protect.
Yeah,
well, I was gonna say one thing interesting in the battery, it looks a little bit askew compared to, like, this is perfectly straight in here. So that's probably just applied manually.
Yep.
And if you're off on that, maybe that could be a place where over time or something just misplaced, something might get in there.
That's definitely a risk. I noticed the same thing, that it's a little cockeyed. Definitely a manual placement. Maybe there's a visual check, but everyone knows the consistency of those can vary depending on operators. I'm remembering one specific scenario with an instrumental customer. It wasn't actually a spacer with a battery, but it was screws that were right next to the perimeter of the battery. And it was found out that operators were accidentally poking the battery during the assembly of those screws. Not enough for them to notice right away, but later on in reliability testing, they found failures, and using instrumental images, they were able to go back, and it was great because they could identify the suspect population, and they could say, oh, it was these 5% of units that had the poked batteries under at risk, and recall just those units instead of having to do a massive recall because all of them could be at risk. So that was a pretty great use case. We could probably actually show. What do you think, Molly? Do you want to show just how that would work?
Yeah, that would be great. I'm going to flip over to another project here. This is a demo piece of our app that we can show. And I'm flipping over this one because we have 250 units here. So we would be able to actually do something like this. So just in a minute or two, I'll show this quick workflow that we could do to figure out exactly what serial numbers were affected by something like that. In this case, I'm going to zoom in on this foam gasket that sits around an LED. And so if I do, let's say, have one example of, either the gasket's totally gone or it's totally askew, and I want to see what other units are affected, all I have to do is basically draw a box around that region. I say I want to find the most anomalous. And now our cute little robot Norm is going to go looking through all of these 250 units, and works the same if this was 250,000 or millions. And he is going to highlight the things that look the most anomalous or the most different. And so in this case, I know exactly which serial number had no gasket. I know exactly which serial numbers had a really askew gasket, and I could go ahead and, I could actually go ahead and push a monitor to directly find these in the field in the future when they get produced this way. And this way I know exactly which units to track back as well.
That's pretty powerful. It really shows the power of collecting that data at time zero and then being able to parse through it. Because if you've got millions of units in the field and you discover a latent failure, then you don't want to have to do a massive recall. If you could do a targeted, these were the very small percent of units, that's a huge win. And we've had a few great examples with our customers. So let's see other questions. Keep posting them in the chat if you have more questions on the battery. I saw a couple other questions I want to make sure we get to. Let's see. So one, I believe we had some insight on that shield can and the two different materials actually requiring it to be welded together instead of actually punched because of the tight radii around that corner. So it was more of a manufacturing geometry limitation, which is really interesting. Let's see, we had another question on how did we waterproof or how did this design waterproof the external buttons and the switch? I think that one was from Mark. Do you have a good image here, Molly, to show?
Yeah, we can jump into that. This was basically, we pulled out one of the buttons. And I think there was also, once this piece was inserted into the housing, there was like an E-clip, right, that came into a groove here to hold it in place. And so I think really these, were these, I can't remember, were these two separate parts here or were these just one part, this orange piece?
The O-ring, I think they're two separate parts. It's a double O-ring.
Double O-ring, okay. Yeah, are you guys familiar with why people do double O-ring designs over single O-ring? I
am not. Please.
Yeah, I'm not familiar. My guess would be, you know, two is better than one. If you have the space, let's put in a backup O-ring. But
yeah.
If you have a better reason, I'd love to hear.
No, I was not familiar. I was curious for you guys, but I kind of agree. You know, maybe if one's not working and you have the space for two, suddenly a double O-ring design. But yeah, it seems this would be a pretty robust way to do that kind of water sealing.
Yeah, again, kind of circling back to the water sealing, because that could be another bucket of concern around what could cause these types of thermal runaway events. We have internal battery, we have some type of puncture, some type of water ingress that could cause shorts in the circuitry could also lead to kind of catastrophic failures like this. My sense would be that these switches with O-rings are going to be more robust, and that really the focus was around the adhesive on the display. And I think I saw a comment in here with some more insight on the type of adhesive. Mark was saying that it might be a laser activated adhesive. That's an interesting one. I don't personally have experience. To me, it sounds like similar to a die cut PSA that then could be activated with more targeted heat around the edge. Has anyone else had experience with laser activated adhesive?
I've heard it as a concept, but that's about it. I think I've heard it as a concept when you're trying to get like a really thin ledge here. Obviously can be super targeted if it's laser.
Yeah, that would be my initial thought is that would be a pretty difficult process to control, to get consistent, because if you don't get the heat up to the desired temperature, then you're going to have a potential weak spot in your adhesive. But it sounds pretty cool if done right. And our experience from trying to take this display off was it was stuck on there pretty well.
Yep.
We had.
Are we missing?
Oh, go ahead.
Are we missing anything? If folks want to chime in on the chat on what are other reasons you might see that thermal runaway?
Yeah, it would be great to hear anyone else's experience or things that you want to discuss. We've got a few questions here on the RF antenna design and where the antenna actually is. We mentioned the other things that are affecting the antenna, but I don't think we've actually found the antenna yet. So maybe we can look for that while you guys post. Let us know if there's anything else. There's still a bunch more components in here There's that board on the back. I think there's some sensors on the back. We have to find the antenna. I think there's some magnets in there. Let us know if there's anything specific you want to make sure we cover.
I think this is the antenna that we're looking at over here, this module here. Is there, Chris, is that what it looks like to you as well?
So one interesting thing about this one is those plastic, that plastic insert or whatever the mold is that kind of goes around and creates those break lines, kind of like you might be familiar with the iPhone series starting with like iPhone 4. They basically use maybe the metal itself from the housing as part of that, but they have this larger integrated shield can system with grounding on the outside, and maybe that plastic spacer there that you're kind of alluding to could also be part of that. But I believe the actual antenna might be the frame of the watch itself. And it's just separated and split into different areas so that they can take advantage of that.
Oh, that's interesting. So that I think you're right there, because that's what that plastic split is for. So I think, Molly, what you're highlighting there is at least the interposer that connects to the housing. So it connects from the main circuit board into that little housing nose, which I believe is being used as an antenna. I think we actually have a picture of just that little antenna piece, if you want to flip to that.
Here's what we're seeing.
So yeah, you have like a gold-plated contact on the edge that's probably touching off right on the edge of the housing, and then transferring that. I think I can see this here.
Yeah, and what was really interesting, one little tidbit that we found was actually on the outside of the device, inside the band slot here. So we're hypothesizing that this is the antenna on one of the sides here. On the inside here, there's a small little exposed piece of metal. It looks like the rest of this aluminum is anodized, but there's a tiny little exposed piece inside the housing here. What do you guys think? Any thoughts on what a tiny little exposed piece of metal inside the housing band would be?
Yeah, I mean, if you're basically taking off the anodize, you're trying to make contact somehow with that. So if there's, I don't know if you're trying to test the antenna, or maybe you're trying to, the band can serve as something else. So maybe you're trying to ground something in the band as well. Those would be my guesses, but I'm no antenna expert at this.
Let's see. Karen was asking, is there a band on wrist monitor? I think you're maybe talking about, is there some type of interface, a smart band, where the device actually interfaces with the band? Let me know if I'm incorrect. I don't think that was available for this. It's just one little contact point. So I don't think they actually had sensors in the band for this one, but interesting thought though. All right, we got about 10 minutes left here. We got a lot still to cover, but please, if there's specific things that you want us to dive into, please post them in the chat here. I know we haven't actually gotten to the sensor board. Chris, are you working on taking out that sensor board in the back?
It's a little bit tough, but it's kind of bonded in there. I'm gonna try my best.
We can, while you're taking it out, we could probably hop over in the app here and just hop straight to the image just to see what's on the back. Ooh, yeah. There we go.
Yeah. Okay, so this is the front side of that board. And we see that one connector to let it speak to the world. And then the back side of this board, I would assume this is heart rate monitor kind of stuff. You guys probably know more about that than I do.
Yeah, I could talk for days on the heart rate monitor here, but I'm curious if anyone has specific questions on this heart rate monitor that I'll address. To me, it looks like, so in the middle, there's an LED package. It looks like there's 3 different die, and you can tell they're different wavelengths here. Typically there's an infrared one and a green one, and sometimes also a red one that's used for the SPO2, which I believe this watch claims to have. So there's 3 different wavelengths there, and there's 3 different photodiodes. So it's shooting the light out from the LEDs and receiving the light in the photodiodes. And that's how you're able to tell the absorption changes as your heart beats, and that's how you're able to tell the heart rate. What's interesting is the photodiodes look different, and in person you can tell they're a little bit different colors. I've got some theories, but if anyone else has theories on why they have different photodiode colors, 2 of them look a little bit purple, and the top one looks a little more blue. Does anyone have ideas on the photodiodes here? What do you, Chris or Molly, any ideas?
I'm gonna have to copy from people in the chat here.
Is it just so that they're tuned to the different wavelengths? Or I don't know. Is that just so that you can catch the different? You want to compare maybe the difference between the 2 different wavelengths and how they're reflected?
Yeah. Ooh, I think Joe is onto something. Peter,
okay.
Peter, I think had a similar answer here: sensitivity to different wavelengths. So I believe that that's likely what they're doing here. They have these anti-reflective coatings on top of the photodiodes. It's like part of this complex silicon process, and they tune it so that it absorbs, let's say, the green wavelength at the highest percentage, and then it actually reflects a lot of the other wavelengths to reduce noise. That's like ambient light coming in from the sun. You want to reflect that as much as possible. So I think that's probably what's going on here. All right, we're coming up on time here, and I know there's a few things we want to cover at the end. There's a couple other questions I want to make sure we get to. We never fully closed the loop on those switches. I know Sam had some questions on the switches. Can we go back to look at where those switches were mounted? How did they do that?
Sorry, which switches are you talking about?
The side buttons on
right. Yeah,
on the
yeah.
PCB.
I think we have a picture of the other side of the board. Let's see.
Yeah, can we go back?
Here we go.
They are SMT'd.
They're SMT'd on the bottom. Wow, I know Sam had some concerns around how they would actually do alignment of those buttons, because again, a lot of tolerances come into play on the board, on the SMT, and then the board assembly to the housing. So that's really interesting there.
Yeah, definitely.
Yeah, I think there's a lot of tolerances here, but I think the board itself may be one of their sort of mid-plane datums, and so you're really talking more about just the tolerance of the board plus the solder thickness, and the connector or the switch itself. So maybe that's sort of how they got around that, or they have a larger tolerance on what that size of the plunger is.
Let's
that's
look
what
at.
I was thinking too.
Oh, sorry to interrupt. We just got rapid fire questions here that are coming in. Karen, can we look at the picture of the back of the watch where we actually see the plastic back cover with the health sensors? I don't think we were actually able to see that before.
Right, this.
Yeah. And you can see the charging pin here as well, which brings up an interesting point of what you pointed out before, Molly. Those on the back of the battery was that spacer to prevent the charging pins from hitting. This is actually a part that would get cycled, thousands of times. Every time you put it on the charging dock, there could be a small impulse. So that, again, another area of focus when you're thinking about what your testing looks like. It's not just a one-time drop event or just during assembly. There's actually a repeated sort of cyclic pressure on that spot.
Yep.
Another interesting thing we can talk about is the the plastic mold on the inside, it's actually the entire cavity is, if I'm looking at it here, is plastic. So if you show the inside where you had maybe the sensor board,
Yep.
like that entire area is plastic, except for some of these little metal exposed bits where the screws kind of go in. And so, you know, this is basically a little sealed chamber, I think, which might help with the waterproofing in general.
Yeah, that's really interesting. I know there are a lot of questions around the waterproofing and the split between that plastic and the aluminum. And I think that probably explains it. So we've got just a few minutes left here. Let's hop over in the last minute. Molly, if you want to show again, I know you wanted to show a follow-up on the app here, but any final questions, please post them in the chat here.
Yep. Right. So we just wanted to show off a workflow around functional test data and doing correlations. You're used to seeing in our teardowns these high resolution images, some of these different key assembly states. So we provide that to our customers for 100% of the units that go down their line. And then we also have functional test data in the app. And so if I hover, I can kind of see what the whole results of the population was. And if I have something that I really want to dig into, you know, let's say we're having this huge antenna problem, I can pull up that specific test and I can actually hop right into our correlations page. This is sort of like, to me, this is every product design engineer's dream, is just being able to see what are the correlations that I have here. So I can go ahead and I can actually just select all the other functional tests that I have in the app. And then it's going to start telling me where it sees correlations. With this functional test failure, it says, hey, in this case, I actually see that most of your failures are coming from, you know, the antenna firmware version 1.64. And so that may be something I can go to my firmware engineer and say, what did you change here? And it can also give you insights like, you know, one of your suppliers is performing worse than the others. All these are things that, you know, I would be typically plotting out one by one into something like Jump. And so to be able to just automatically have instrumental plot everything against a root metric here, and then pull to the top the things that are the most likely correlations, I think is really helpful. And then in addition to those test correlations, we can also say, hey, what do you see that's visually different about these, you know, 32 units that are failing this test? It's kind of what you would do. You would gather up all these parts, you would tear them down, and then you would be like, darn, what's different about these? And so instrumental looks through all your pictures the same way, and it highlights if there are specific regions that you should really, that, you know, our AI doesn't know that this is a grounding tab that does, you know, it is a part of our antenna system. But it does know that when this region is empty or the pin is bent like this, then, you know, there's a strong correlation with this functional test failure. If that's my problem, maybe I just found my root cause. If not, I can scroll down to the next one that's also very likely correlated. So yeah, just a quick teaser of the kind of workflows that we help people achieve with instrumental. And with that, I will stop sharing and hand back to Tobias for some final remarks.
Thanks, Molly. That always gets me excited. Just the sheer number of hours that I spent in Jump or in factories doing failure analysis that could have been answered in seconds is pretty crazy. So super excited about our new correlations feature. We're right at time here. I know there's a lot of stuff that we didn't get to, but good news. If you want access to all of these images from the teardown, we've got these 10 different products now. You have not one, but two options. Best option, our in-person event in June 16th. We're going to be doing an in-person teardown, Amazon Echo Show. It kind of looks like a HomePod with a display on it. It follows you around the room. I've been playing around with it, so it's pretty fun. We're going to be tearing that down live, and we're going to have all these old devices just laid out so we can look at all the different parts. So either come in person or you can also email us communications@instrumental, and we can get you access to the virtual teardown library as well. So either one, survey at the end, let us know what you want us to tear down. You guys asked for the smartwatch, and here we are today. So fill out that survey and we'll see what we got up next. Otherwise, yeah, we're super excited to see you guys at the in-person event. Thank you all for joining. This really is, it's all about the feedback and the questions. So thank you for all your participation, and we will see you next time in June.
Thanks, everyone.
Take care.
Manufacturing is changing, and keeping programs agile and on schedule is harder than ever. Leading engineering teams rely on Instrumental to find issues earlier, fix them faster, and make sure they don't come back. Experience the first manufacturing optimization platform designed to enable continuous improvement of your process, from development through production, by unifying your data so your teams can make decisions faster. Instrumental makes finding correlations in product data easy, so your engineers can spend less time wrangling data across email, spreadsheets, and internal systems, and more time solving problems. It's simple. We put the right data in front of the right people in real time. Instrumental aggregates images of every unit at key assembly stages, parametric test data, and measurements in real time in a secure, managed cloud. When installed across factories in a supply chain, brands and suppliers are able to work together to solve their most complex issues. From your first build, Instrumental's Discover AI proactively identifies new issues by scanning your products for anomalies and automatically delivering a daily queue of issues. Engineers can jumpstart failure analysis with defects in context. Engineers leverage a rich, remote dataset to quickly identify correlations and potential root causes, and can push live tests to validate solutions immediately. They use Instrumental to eliminate issues at the source and make sure they don't come back. With complete build and issue analytics for the entire team, program leads can kickstart daily stand-ups, streamline executive reporting, and communicate seamlessly with global teams. Instrumental has helped leading engineering and operations teams move faster, improve yield, and build better products from proto through production. Better products start with better data. Better products start with Instrumental. Schedule a demo today